All right, up next, let's see what we have. Oh, thank goodness, this time they just want me to write the hypotheses. Okay, so let's see here. So notice here it says each of them took a random sample. Now what that means is we have two samples. Wait, sorry. Yeah, so since we're taking two samples, it's not going to be a paired test. We'll talk about what that is, but we're doing a two sample test, and notice they're just trying to see if there's a difference in price. So not one exactly being bigger than the other. So two samples and just different. Oh no. Something about 4:30 a.m. always makes these videos go really, Khan Academy go really slow. It's like when they do their updates or something. It could also be that I'm trying to upload a video right now. I'm just surprised it's eating up that much memory. Okay, so up next, this time they're asking about did we get all our conditions for inference right? And this is a mean comparison. And when you have a mean comparison, let's see here. So a football team is 40 players. They took a sample of 20 players. They reported how many hours they slept. Okay, so it did say they took a random sample. Do we satisfy the normal condition? Let's see here. It says each player also reported. Okay. Well, actually, I don't think I can check this because there aren't both samples. There's just one sample that we broke up. So I'm a little iffy on this. Both samples satisfy the normal condition, though. It says there were some extreme outliers in the data. Now, based on that, what that means is it's not going to be, symmetric without outliers. And notice our sample sizes are small, so therefore we definitely can't satisfy the normal condition. Can they be considered independent? Also no, because if we have 40 players total, we sampled half. So I almost want to say that none were met, but I guess I can't. So I guess I'll say that they were random. But we didn't satisfy the normal condition because if our sample size is small, less than 30, we need to make sure that there's no major outliers in the data and that it's roughly symmetric is the words you're looking for, or that you want to put on the FRQ. Can they be considered independent and the samples themselves independent? Definitely not, because he only took one sample and split it. That's already not dependent. But also, look at how many he sampled. 50%. That is way more than 10%. Okay, it's kind of moving quickly again. All right, next, just find the test statistic. Hooray, awesome, love this. Now, what are we doing here? So notice, read the wording here, they took a random sample of adult males and surveyed their exercise and sleep duration. And so it looks like what we're doing is, okay, so it's one sample, and essentially what we're doing is we're blocking by people who exercise and don't exercise. Now what that's really doing is that is what we call a, well, let's just see what's going on here. I don't want to talk out of turn. Well, it's one sample, and we blocked. Okay, but we still have a large number, so let's go here. So we have, obviously we should be doing exercise minus no exercise, so that should be a given. Minus the expected 0, which you're not really going to see. So it could be A, C, D, those, because those are going in the correct order. Up next, let's talk about the standard deviation. The standard deviation, again, we should see this kind of behavior right here. So 1 over its sample size and 180 over its sample size. It looks like we're looking at, this is the correct answer. And it's slow again. Okay, so it turns out you are allowed to take one sample and block them and call that a two-sample procedure. But again, they both need to be sufficiently large. So that clarifies what I was thinking about earlier. Okay, up next, finally, quick question. Is it higher in 2017 than it was in 2016? Hooray. HO should always imply equality, so throw out D. Which one shows 2017 higher than 2016? That one. We're almost there. Just 3 more after this. But my computer's being slow. I'm sorry. Just trying to see if... No, I can't really close anything. Alright, anyways, this time, same idea, they want me to calculate the p-value. So this is definitely going to be a big example to cut through. But here we go. So it's n minus s, so I'm just going to jump into finding the t statistic, because when you're comparing means, it's a t-stat. So n is the 64.3, minus us is 53.4. That's minus the assumed 0. You're expecting the difference to be 0. So you're always doing the actual difference minus the expected difference, which is 0. And that gets divided by, we have our standard deviation, which is the first standard deviation, so it goes in order. Notice if 64.3 leads, the first standard deviation in the first sample size is going to lead. That just shows them that you're aware that you're doing things in the right order. Then we have the 23.9 squared, make sure you square it, over its sample size 75. Let's calculate what this is. All right, again, make sure you simplify the numerator first before you start dividing. So 64.3 minus 53.4 minus 0 doesn't really matter. Now divided by big square root, 18.2 squared over 65 plus 23.9, make sure it's still in the big root, squared divided by 75. And it looks like our t-value is 3.06 if you round. Now, we have to round to 2 places. So you can put approximately if you want, because you are rounding a little bit. And now let's find the p-value. Now we're doing a not equal to test. So what does that mean? Not equal to test means we expected 0. We got 3.06. Now the p-value, again, is always saying how rare was your result, or an even rarer result, what were the odds of that happening? And since it's a not equal to test, we have to multiply that by 2 to account for it could just as likely in a not equal to test be that far on the other side. So let's find just 3.06 for the t-value. And the other thing is, let's look at our sample size of 65 and 75. We'll essentially be looking at degrees of freedom 60 there. And we're going to try to find where that 3.06 falls in between. And it falls in between here, which is, at first, the p-value is a range between, let's go smaller to larger, 0.001 and 0.00, or I should say it like this. At first, the p-value is in between 0.001 and 0.0025. Now that's only for the amount above. Now we have to double that, so we're actually looking at something between 0.002, that's that value doubled, and 0.005. Excuse me. Let me just make sure. Okay, so that's what we should be getting, something between 0.002 and 0.005, and that is still less than 0.01 in general. All right, now while the computer loads, let me show you how we can do this in the calculator really quickly if you do have one. Again, we're doing a 2-sample t-test. Whoops, not interval. 2-sample t-test. Here it is. Yeah, I got it. Okay. Now, x1 was 64.3. Standard deviation was 18.2. Sample size was 65. The next one, 53.4. Sample size was 20, or standard deviation was 23.9. Standard deviation, or sample size was 75. Hello. And we're just doing a simple not equal to test. Pooled as always no. Calculate. And there's our test stat, 3.075, which is around to 0.306. And we get a p-value of 0.00269, which is indeed between 0.002 and 0.005. So there you go. So notice the calculator is going to give you a precise value for the p-value. By hand procedures just give you a range of p-values, and you do have to double those. So just be really careful of that. Now see, notice if you didn't double, technically, look at this. 0.0026 isn't even in the range. So that's kind of a clear indication that you do have to double it in a not equal to test. All right, 2 more questions. See if we can do this somewhat quickly. Okay, awesome. We've talked about this before. They're trying to do a not equal to test. In other words, we're trying to show that there's a clear difference between the two. Now, also, they give us all this data and they give us the 95% confidence level. So 95, alpha 0.05, those are related to 100%. And so notice this confidence interval does not contain 0. And in fact, it's all positive. Now, how do you get a positive number by subtraction? The larger number went first. So in other words, this 95% confidence interval is saying clearly the mean for Bosk is greater than, because you only get positive values from subtraction, the mean for Anju, or however you say that. So that means there is a clear difference. We can conclude the difference. So that means the p-value is less than 0.05. P-value is less means you can conclude, or there is evidence. Those go hand in hand. They have to agree. You can't say B. That's nonsense. If P is less, then you should always be rejecting. So they're like mishmashing those. So make sure that's clear. But anyways, p-value is less, so we can conclude there is a difference. This is clearly one-sided. It's always positive. So USB was always above. Oh, you know what? I'm not charging my laptop. That might help speed things up. Let's see if it speeds up now. We've got one more question anyways. Okay, last one. And we want a 99% confidence interval. So again, we're going to do this by hand. I'm going to go really quick. We're doing proportion of Republican minus proportion of Democrat. So let's go. Proportion for Republican is 150 out of 600. Now trust me, that's 0.25. You might want to write that down earlier though. If it was FRQ, 80 out of 400 is 0.2. Trust me. Plus or minus. Now this time, 99%. This is proportion comparison, so that's just the z value. So 99, we'll use 2.576. The z value is always at the bottom of the t chart. Okay. And now we just need that big old ugly standard deviation, which involves p of, actually no, it doesn't, because we're doing a confidence interval. Now this is a big point. Confidence intervals don't rely on any assumptions, all right? Testing relies on assumptions. So in other words, in a proportion test, you're not going to do, hopefully we can see that here in the reference sheet, in a proportion test, there is no assumption, so you have to use this formula for your standard deviation. And see, this one says when you're assuming they're equal. In other words, when you're doing a hypothesis test, this is what you use for the standard deviation. So we actually haven't seen using this yet, but now we are. So the way this is going to work is, well, we can see that the first one was 0.25. 0.25 minus 1, or 1 minus that is 0.75. Over the sample size that 0.25 came from, well, that was the 400. No, it wasn't. It was the 600. My bad. Be very careful. Then we have the 0.2. That difference from 1 is 0.8. And it was over the 400. So that's how we're going to find our interval, and we'll plug this into the calculator. One thing you might want to do to make things faster for yourself is just do the 0.25 times the 0.75 over 600, plus the 0.2 times the 0.8 over 400. And then that way, we can just do this a little bit quickly. 0.25 minus 0.2, let's first do minus 2.576 times, I'll just round to 0.0669. 27. I'll give it a little extra. You always want to, technically most answers get rounded to 4 places, so you might want to go a bit further in your, what we call like intermediate work, not your final answer. So notice I've written it in a very nice way that I can just press answer and get something for the lower bound, and all I have to do is backtrack, copy it, and press plus, and now I have the upper bound. So I'm looking essentially between negative 0.0189, okay, and 0.119. So there was the correct answer. All right, last but not least, just for the sake of it, how do we get this in the calculator? Well, let's do that. Stat. It's in tests, but it's a 2-prop z interval. There it is. Let's scroll down a bit for it. Now, x1, Republicans went first, so it was 150 out of 600, and it was 80 out of 400. And see, this is what I absolutely love. Look at how easy this is. You just have to type in that immediate data, say that this is what you put into the calculator, and you get the whole interval for free. It still rounds to what we got in the A, but think about how much faster that was. But if you don't have a calculator, you need to know this formula, and you need to know when you're either using this standard deviation for an interval or this standard deviation because you're using testing with an assumption that they were equal. Okay, and that's it. Took a little longer to get through this video, but I would imagine you could probably see this one on FRQ in the AP exam. Hopefully this helped refresh the ideas going on behind the scenes. Hopefully seeing all these units mashed together helped you see some of the overlapping ideas going on. Best of luck, keep on studying hard, and knock out that exam.